guys, it's your boy Ian, and today we're going to be measuring the speed of light using a microwave, a piece of chocolate, and an egg.
John, if you don't mind me asking, do you have any interesting facts about the speed of light?
Well, the interesting thing about the speed of light is that your frame of reference does not matter. In physics, the frame of reference is your relativity to the object at which you are observing the velocity of. When it comes to an object in motion, one person may see it as an object moving very fast, while another person may think it is not moving at all, as it is relative to their location. However, when it comes to the speed of light, a person's relative location in comparison to the light will not matter. The speed is the same no matter where you are observing.
So for our first experiment, we're going to be using the chocolate bar, which is going to allow us to calculate the wavelength that is created by the microwave.
So, Mr. Wheat, what are microwaves?
Well, Dan, microwaves are a form of electromagnetic radiation, but they are beyond the visible spectrum, so we cannot see them. A microwave oven works by creating a standing wave in the microwave, and the turntable is included so that this standing wave reaches all portions of the food that you are heating up.
To do this, I'm going to be, of course, using the bar of chocolate, this ruler, and the microwave.
John, I'd also like to ask, would you be able to go into more detail about the antinodes and nodes on the wave diagram?
Well, as seen in the diagram, the distance between the two antinodes represent 1/2 of the wavelength. The antinodes are located at the peak and the trough of the wavelength. The peaks are at the highest point, while the troughs at the lowest point. On the other hand, the nodes are located at the equilibrium line of the wave, and in this experiment, we will only be finding the antinodes.
Now that we start the experiment, we have to put the chocolate bar face down into the microwave so we're able to perfectly visualize the nodes and the antinodes that are created. When I put the chocolate bar in, the turntable has to be off because if it was rotating, the chocolate bar would melt evenly and we don't want that to happen. At this point, I'm going to turn the turntable off and set the microwave to 15 seconds. As you guys can tell, I already put my finger in the two spots where the chocolate bar is melted. And if you closely see, if you measure from the end of this one spot, end of this spot to the end of this spot, it's exactly 6 centimeters, which represents the distance between the two antinodes, which also gives us half the distance of the wavelength. So we have the wavelength equals 6 centimeters, but this is only half of the wavelength because we measured the distance between the two antinodes at a peak and a trough. So 6 centimeters times 2 equals 12 centimeters. So wavelength equals 0.12 meters because we want our final velocity to be in meters per second. So to get the velocity, we need V equals F times wavelength. So to carry out our calculation to know frequency, it is given to us on the microwave. And as you can see, the microwave frequency is 2,450 megahertz.
What is frequency?
The frequency of the wave is the number of waves that pass a fixed point in a given amount of time. The frequency of a wave is able to be measured by counting the number of crests of a wave that pass the fixed point in 1 second or some other time period. Frequency is measured typically in hertz, but in this experiment, our frequency was given by the microwave in megahertz, which we then converted to hertz. With frequency, the greater the number, the more waves there are in that amount of time.
But why is the frequency important to our experiment?
The frequency is important to our experiment because of the equation velocity equals wavelength times frequency. The frequency is given to us once again by the microwave.
How we find F is given on the microwave, which is frequency equals 2,450 megahertz, which this equals 2,450,000,000 hertz. So now, since we have wavelength and we have frequency, we can now find our final velocity. So we do 0.12 meters times 2,450,000,000 equals velocity, and our final velocity comes out to be 294 million meters per second. So we have this final velocity of 294 million meters per second, and the actual velocity of speed of light in a vacuum is 299,792,458 meters per second. But the difference is that the medium that the light is going through in this answer is through air, but the medium that the light goes through in this answer is a vacuum, so the answers are going to be a little off.
So to carry out our second experiment, we will be using an egg and this microwave. And with this, we will be able to support our answer from the previous experiment, which was with the chocolate. To prepare the egg for the microwave, we will need to separate the egg yolk from the egg white. With this, we will be able to see the two antinodes that appear. So I will now put the eggs in the microwave. I will make sure to turn the turntable off because we do not want it to cook evenly, and I will set the microwave for 25 seconds. So we will now be measuring the two centers of where you can see the egg being cooked. From this, we can see that it's about 6.5 centimeters, which we will use for our calculations. So from the two cooked portions of the egg, we were able to get the half wavelength of 6.5 centimeters. Since this was only a half wavelength, we need to multiply it by 2, where we get a wavelength of 13 centimeters. To find the velocity, we need to convert this to meters, which is 13 centimeters equals 0.13 meters. Velocity equals frequency times wavelength. From the description on the microwave, we got frequency equals 2,450 megahertz, which equals 2,450,000,000 hertz. So now with these numbers, we are going to multiply 0.13 meters times 2,450,000,000 hertz, which equals the velocity. Now when we put this into our calculator, you get 318,500,000 meters per second. So once again, the true value of the speed of light is 299,500,000 792,458 meters per second. There is a difference in our answers because this is going through air and the true speed of light is through a vacuum. So why do our two experimental values from our experiment differ from the typical constant we use for speed of light in our own physics class?
Well, our answers were slightly different because when a light enters a denser medium, the speed and wavelength of the light decrease while the frequency stays the same. But the constant that we used in class was measured through a vacuum, and light travels the fastest in a vacuum. That's why it was slightly different. So today I'm here with Dan and Ian.
What's up? I'm Dan.
And I'm Ian.
And we're gonna show you a visual representation of a standing wave.
So when you put your food in the microwave and turn it on, a standing wave is immediately put onto one portion of the food. This one portion is heated up at only one point, and that is why microwaves have a turntable so that this standing wave is applied to all aspects of the food when it is rotating around it. This standing wave is absorbed by the sugars and fats and water in the food, and that is how your food is heated up. So we're going to show you a representation of the standing wave that's applied to the food.
So how do you guys think the experiment went overall? We'll start with you, Ian.
So for my experiment with the chocolate bar, I feel like it went pretty well. The final velocity that we got was pretty close to the true value of the speed of light. But the only thing that I would change is that we would have figured out a good time for the chocolate bar to be in the microwave, because we kind of did a guess and check to see where we could see the two antinodes had melted.
Yeah, so I'd say the same for my experiment. When we cracked the egg, we got the egg yolk, but we did it in a bowl. So the problem with the bowl is it doesn't give enough of a distance to measure the two antinodes. So next time I would have done it on a more flat of a bowl so that the egg yolk could spread out farther, and in that case we'd be able to see the antinodes more. Also with mine, the time was a problem. With the amount of time I did, I had trouble finding the exact antinodes because either I'd cook it too much, or if I cooked it too little, you wouldn't be able to see them at all. So yeah, next time I'd improve on the time. John, how did you feel?
It went pretty well.